So we're going to review multiple regression, specifically the regression coefficients. So looking at multivariate issues with prediction and whether we're meeting assumptions. We're going to kind of review the predictability of multiple regression models and then talk about how we actually create and interpret categorical variables, higher order trends, nonlinear, and interactions. So as a reminder, multiple regression suggests there are two or more predictor variables. So if we have two continuous variables and all we're looking for is a pattern or a correlation, that's correlation. If we're adding a predictive element, that's simple regression. And multiple regression simply means we have more than one predictor variable. Now again, if we have a series of variables that will fit a different statistical technique, we should use it. Multiple regression allows us to look at just about any possible combination, but there's a cost. It's not as rigorous and it's not as likely to find effects as more tailored statistical analysis. So for example, if you had a continuous outcome and a bunch of categorical variables and only categorical variables, you'd want to use an ANOVA. If you had multiple continuous outcomes, you'd want to use a MANOVA, which we're going to be talking about later in this class. So multiple regression is where we go when there is not another appropriate statistical technique. But multiple regression is what we mainly want to focus on as far as our knowledge and our understanding, because it allows us to do so much with just about any combination of variables. Multiple regression probably also is one of the more used techniques because of its predictive aspect when we're actually looking at applied settings. Also, with applied settings, a lot of the times we don't really get to control the variables we're handed, and we're given variables that would not fit anything but multiple regression. So just a reminder, the variables that we can include as predictors in a multiple regression include linear trends, so those are continuous variables, or a categorical variable with only two levels, a dichotomous variable. Covariates, so variables that we're actually not interested in. In fact, we want to remove their impact on the outcome to give us a clearer picture. Those variables, no matter what they are, can be either continuous or categorical. If they're categorical, we can dummy code them into dichotomous variables to allow them to be inserted into a multiple regression. Now notice again, this is an inelegant solution. If I've got a categorical variable with 5 levels, I'm going to have to create 4 dummy codes. I'm going to have to take that one variable and make it into 4 variables in order to include it in a multiple regression. That's eating up a lot of power, and that's eating up a lot of potential interactions in a multivariate model that I may not want to account for. So again, if I just have categorical variables, there's a better way to do that than a multiple regression. Multiple regression, though the assumption is linear trends, we can create nonlinear trends to test that as well. And finally, we can look at the interactions between multiple predictors to see if there is something beyond an additive effect. Now, when we're looking at multiple predictor variables, that means we also need to consider how the predictor variables relate to each other and the outcome. So how predictor variables relate to the outcome is pretty straightforward, but what can actually occur is the combination of predictors may still result in a violation of the assumptions, and we're going to talk about that in a little more detail in just a few slides. We also need to ask the questions of how does the predictor variables relate to each other, and does each predictor add incremental validity? In other words, as we add predictors to the model, does each predictor explain more of the unexplained variance in the outcome? There's really no value to having multiple predictors that are all predicting the same variance in the outcome. And finally, of course, we also want to make sure that predictor variables are not highly related to each other, because that can also create problems in our prediction, and it also, again, just eats up power. So the assumptions of multiple regression. We still have the initial assumptions we already talked about last semester, which is the descriptive statistics. So we want to check every continuous variable, whether it's a predictor or an outcome, to make sure it's normally distributed, it's not skewed, it's not kurtotic, and there is no major outliers. But just because an individual variable passes this bar, in other words, it passes these tests and it doesn't violate the assumption, that doesn't mean that it may not combine with other predictors to create a problem. The way we look to see if there's a problem in the multiple predictors on the outcome is the residual plots, and we can ask for these in SPSS. So we're looking at the y-axis, which is the residual. So we're not looking at the strength of the prediction, we're looking at the strength or the amount of error in the prediction, and this is being estimated by SPSS using basically the standard error of the estimate. So we're looking at the x-axis being the predicted y, the value of the criterion predicted by the model. So what we're looking at is not any one predictor variable on the outcome, but the entire model on the outcome. And patterns in the residual plot indicate that we may have missed something in our model. So we're looking at these to see if there was a problem. In other words, did we violate an assumption at the residual level of the overall model, the multivariate model? So we're first going to look at an actual residual plot is what we're wanting to see. So again, we're not looking for a positive or negative relationship here because we're not looking at the strength of the relationship. We're looking at the amount of error in the prediction of the combination of predictors on the outcome. So we're looking for a straight line off of 0, 0 being a perfect prediction. So any dot that lies on the 0 line means that it was dead on. There was no error or estimate to that. However, each dot above the line represents an overestimation, predicted y, and any dot below the line means an underestimation. So this would be a good example of our assumptions have been met. The residuals are roughly and evenly distributed. The residuals form a horizontal line. This would be an example of there was no additional problems when we went from individual predictors to a multivariate model of multiple predictors on y. Now we're going to look at some examples of residual plots that tell us something's gone wrong. So if we have a residual plot more like this, we have a violation of normality in the multivariate model. And again, when I'm saying multivariate model, I'm meaning multiple predictors all predicting a single outcome. So the residuals have a greater spread to one side of 0 on the y-axis. So for example, in this case, we are seeing that there is not a lot of error when you overestimate off of y. There's a lot of error when you underestimate off of y. So the r squared here may be too large or too small. So in the case of any prediction that's above the 0 line, r squared actually is a little small. It should be bigger. That's a strong relationship that we're seeing there. There's not a lot of error when we go above the predicted line. The r squared, however, is actually too large for the bottom prediction. So anything below the line of 0, anytime we underestimated y, we're actually claiming a stronger r squared than there is. And again, r squared is simply that effect size, how much variance in y was actually predicted in our model. Now in this case, generally speaking, what we're going to have to do is log transformations, because what this usually represents is that we have multiple individual predictors that passed the bar individually, that they were not skewed, but each one was close. And in combination, they actually now, in the multivariate model, pop over that line. And that's what this is representing. So just like any skewed variables, we may have to do log transformations. We may have to go in and find some outliers. We're going to have to do some exploring to figure out where this is coming from. And again, the residual plot simply tells us there's a problem in our predictive model. The more complex the model, the harder it's going to be to figure out what were the variables that actually are causing this. We may have to do some back and forth checking of the model. We may have to transform a few skewed variables, see if that fixes it, rerun the residual plot. So there's definitely some back and forth that occurs when a residual plot is found to be in error, that there's a problem. The simpler the model, usually the easier it's to find. So for example, if this was an example of simply two predictors on an outcome, there's a pretty good chance I'd know I've got outliers in both of those samples. If I remove those outliers, this may go away, or I may need to log transform both of the predictors. If I've got a model with 7 predictors, I may have to do a little bit more detective work. So this is again an example of we probably had near nonlinear terms individually in our prediction. So when we were looking at each predictor on the outcome, we may have found, some evidence we might need to check for a nonlinear form. We went ahead and created a nonlinear term, but it wasn't needed, it wasn't significant, so we dropped it from the model. But then we run the residuals and find we probably did need those nonlinear terms. So the residuals take a nonlinear form in their prediction, and again, this is the multivariate combination of predictors. Again, we may underestimate the relationship between the model and the criteria depending on where we look in the model. And again, the way we're going to test this is we may need to create nonlinear terms, and we may have to create multiples of them to find out where this is actually occurring. We could find heteroscedasticity in our residual plot, greater residuals at some values of y than others, generally a shotgun pattern. Again, our effect size may be underestimated, may be overestimated, but generally underestimated. And mainly what we're saying here is there actually is something important going on, it's just we're currently not catching it. Usually what this is going to represent is that we have an interaction that we should have been measuring. Now, if we're lucky, we actually have the terms that are interacting. We have those as variables, and we simply need to create an interaction term. Though we may do that research, we may look for those interactions and find after checking every possible interaction, we're still getting this result. What that means is that our predictors are interacting with something we didn't measure. That may be a sign we have to go back to the drawing board and maybe do another study with more predictors, more measurement. And finally, we may find examples of an outlier, and again, a multivariate outlier. So when we examine those residual plots, we may find the residuals are generally evenly distributed, but we've got a couple of departures. We've got a couple of extreme scores. And again, we may have to either do transformations of the data, or we may have to go in and find individual scores that need to be reduced. So it may be an example that we can pull out a single outlier from one of our predictors. And again, it wouldn't have been an outlier that we would have removed individually. It was an extreme score that didn't pass the bar to be called an outlier originally, but it's creating an outlier prediction. Now, it may be that we can get rid of one. We may have to get rid of a couple outliers from a couple of predictors. Again, it's going to take some detective work.